Ellingham's diagram is a graph of standard free energy versus temperature. Ellingham diagram is used to select, predict and elect the best and the most suitable reducing agent. In metallurgy, we have come across plentiful reducing agents. Most common reducing agent is carbon, but we understand that the choice of the reducing agent is dependent on the nature of the metal oxide. Therefore, Ellingham's diagram is helpful in gauging which is the best and the most suitable reducing agent. It is a graph of standard free energy change versus temperature. Hope you have understood the first point and the first characteristic point about Ellingham's diagram. It is a graph of standard free energy change versus temperature. With increase in temperature, delta G naught value increases. It slopes towards upwards in this fashion. I have negative values and then one which is parallel to the x-axis, that is for carbon dioxide. I once again would like to tell, as the temperature increases, the curves slope upwards. Wherever there is a change in the slope of the line, at that point it undergoes phase transformation. Wherever there is a change in the slope of the line, it undergoes phase transformation. I again would like to suggest and tell that in this we have got the clue to attempt for this question. In Ellingham's diagram, delta G naught value increases with increase in temperature. Looks absolutely right, but not at all conditions. Looking for the next. Delta G naught value is positive for mercuric oxide at all temperatures. But I would like to say one special point here. Delta G naught value is negative, it acts as a good reducing agent. Delta G naught value is positive, cannot act as a reducing agent, and it depends upon the temperature condition here, not at all temperature. More negative the delta G naught value, greater is the reducing power of the element. Absolutely right, following to the context of my question. Therefore, the most appropriate answer for this is option C. More negative the delta G naught value, greater is the reducing power of the element. Dear students, as we discuss these questions, we shall also sum up this chapter systematically. These questions already we have discussed in a different way. I had repeatedly been telling this in my previous classes also, that the success in CET does not depend on how many questions you are segregating and reading, but how many techniques you have adopted to approach for that question. In this, purification of bauxite is done by, I remember telling these words again, in the metallurgical processes that we have, the first stage is concentration of the ore. Concentration of the ore refers to removal of impurities. Second stage is reduction, converting a metal oxide into a metal. The final stage is refining to get the metal in 100% pure state. The purification of bauxite is done by, I have given levitation, leaching, electrolysis, magnetic separation. If you could remember, concentration of the ore, methodology of removal of impurities. Concentration of the ore, examples, first step, gravity separation, hydraulic washing, lavigation. This is the methodology it is employed if my impurities are lighter in nature. Repeating my statement, if the impurities are lighter in nature, the method that we employ is hydraulic washing, gravity separation, or it is lavigation. Second one that I have is leaching. This leaching is known as a chemical method. Leaching is employed for concentration of bauxite. Hope you got the clue now. Leaching is a chemical method. Leaching is employed for the concentration of bauxite. In this, the bauxite is treated with sodium hydroxide. You get sodium aluminate. Next process, electrolysis. Electrolysis is done for copper. Electrolytic refining of copper, we had discussed it earlier. Magnetic separation is employed if either the ore or the impurities are magnetic in nature. In all, this question summarizes all the concentration technique. Quick recap. Concentration of the ore refers to removal of impurities. First stage of concentration. Hydraulic washing, gravity separation, lavigation, all are one and the same. This method is employed if my impurities are lighter in nature. Magnetic separation is employed if either the ore or the impurities are magnetic in nature. Leaching is a chemical methodology of removing the impurities. Purification of bauxite is done by chemical methodology, that is leaching. Therefore, the right answer is option B. The next question. The role of pine oil in froth flotation process. I hope we have discussed a couple of questions on this, but we never discussed about what is the role of an oil there. I remember a little while ago mentioning some 5 golden words, that is tank, oil, water, air. If I happen to approach for this question, you are taking the tank, you are mixing the ore with oil and then water, you are blowing air. When you blow air, the impurities are wetted by water. Ore is wetted by oil. Repeating my words, impurities are wetted by water. The ore is wetted by oil. Therefore, preferential wetting takes place for ore as well as the impurities. Now, when I mix it up, when I mix the ore with oil and then water, the role of oil, is it a collector, is it a froth stabilizer, is it a depressant, or it is a coagulant? Coagulant ruled out. Collector, froth stabilizer, depressant. I would like to tell about depressant. Depressants are those which are used to separate 2 different sulfides present in it. Example, sodium cyanide is used as a depressant to separate ZnS and PbS. Sodium cyanide is used as a depressant to separate ZnS and PbS. That may not be the right answer. Coming back to froth stabilizers and collectors. Froth stabilizers, the word itself says, froth is stabilized by adding xylol, xanthates, etc. Collectors, I would say pine oil, the best role of pine oil is it acts as a collector. Hope you have understood this. The right answer for this question, the role of pine oil in froth flotation process is it acts as a collector. Option A is right. We'll move on to the next question. In the extraction of iron, charge is the mixture of. Little while ago when we were discussing about extraction of iron, some finer points about extraction of iron. Iron is said to be the king of metals. Iron is extracted by blast furnace. In blast furnace, we have various zones: zone of combustion, zone of reduction, zone of slag formation. Hope you have recapped it. In this blast furnace, when I take the ore is concentrated. The concentrated ore is mixed with limestone and coke. This mixture, I addressed it little while ago as charge. Hope you have understood it. What is charge? Charge is a mixture of limestone, ore and coke. I am aware that you are now clear that coke acts as a reducing agent, limestone acts as a flux. Again, I remember telling the role of flux. Flux can either be acidic or basic or neutral in nature. Again, we remember discussing about reducing agent. Carbon is not the only reducing agent. Depending upon the nature of the gang, we choose the reducing agent. Therefore, the right option for this question in the extraction of iron, charge is the mixture of concentrated ore, limestone and coke. Therefore, option B is the right option. We'll move on to the next question. In the electrolytic refining of copper, pure copper is deposited at, it is a final stage of recovery of a metal. In the final stage of recovery of the metal, we have an electrolytic tank. In the electrolytic tank, you have taken the electrolyte, that is copper sulfate. You have taken anode and cathode. Anode is made impure, meaning anode is impure copper. Cathode is for the deposition of pure copper. On electrolysis, the impurities will settle down as anode mud, as discussed in the previous question. Anode mud will contain a mixture of gold and silver. Pure copper is deposited on cathode. Repeating my word, in the electrolytic refining of copper, pure copper is deposited on cathode. Impurities settle down as anode mud. Anode is made the impure copper. Therefore, if I happen to read the question, in electrolytic refining of copper, pure copper is deposited at cathode. By chance, if I happen to squeeze on a plentiful questions from this, which is the electrolyte that is used in the electrolytic refining of copper? It is copper sulfate. What is the composition of an anode mud? Anode mud also contains minute traces of gold and silver. Hope you have understood. Option B is the right answer for this question. My dear students, as you have thoroughly looked in couple of questions in this chapter, every question you have something, a learning exercise. As you keep on repeatedly reading, for every question you can constructively make a plentiful options or plentiful questions depending upon how you have learned. My sincere advice to you is, as you scroll through the pages of metallurgy, read back the techniques that are being employed. Look in for the ores, look in for their chemical combination, look in for the alloys, where they are used, look in for what all special techniques have been employed for the extraction processes, and then learn systematically, rewind couple of times. Metallurgy, you should get something out of it for the CET. Best wishes for you. I hope you will do well, and I am there always with you to help you, guide you, and may God's almighty blessings be showered upon you. Thank you.